Hi, my name is Ariana, and this is my video lab report for Physics 2211 with Dr. Paduka, Lab 5, the falling slinky. The purpose of this lab was to measure and predict the motion of a stretched out slinky dropped from rest by comparing the observed motion with a computational model. The results for this lab are shown to the left, and as you can see, the observed model deviates slightly from the predicted model. Here are some background concepts before we get into the lab. The first important concept is Newton's second law in the form of the momentum principle, which is used to derive the velocity update formula that is used in the computer model and seen below. It relates the net interaction between the system and surroundings to the observed motion of the system. The formulas below were used in the computer models that predicted the motion of the object over time. The main forces involved in this experiment are gravitational force, drag force, and tension and applied force due to the slinky. The formulas for the forces are shown above and used in the computational model. The net force is the summation of the gravitational drag and slinky force, where the gravitational force is negative, the drag force opposes gravity and is therefore positive, and the slinky force changes directions as seen by the free body diagrams. The free body diagram on the left shows when the slinky is let go as the force of gravity and tension force from the top of the slinky balance out, resulting in the bottom of the slinky remaining at rest. The free body diagram on the right shows the object once the top of the slinky catches up with the bottom of the slinky, where the drag force opposes both the force of gravity and the applied force of the top of the slinky. In this experiment, the system was the slinky and the surroundings were the Earth. I chose the tracker model so that the origin was at the bottom of the slinky and the y-axis was collinear with the slinky at its rest position. I tracked the model beginning from when the top of the slinky was released from hand, and in this model I assumed the calibration length and mass from the internet using the measurements of a standard slinky. I also assumed the drag coefficient through trial and error. Here are the initial conditions I set in my computer model. I linked the rest of the code in the slide if you want to take a look at it. I set the mass to 0.25 kilograms as the internet provided that was the mass of a slinky. And the initial position was the origin as that was one of my assumptions, and the constants are either known or estimated through trial and error. This part of the GlowScript code is inspired from Lab 2. In this section of the code, I first established the forces, in this case the force of gravity and tension. And I calculate Fnet, which is just summing the two forces, which is then used in the position and velocity update formulas in order to update the slinky's position. I repeat the process of calculating Fnet and then using the position velocity update formulas to find the new position for the time after the top of the slinky makes contact with the bottom, and this time I include drag force in the Fnet and disregard tension force. All of this combined gives the y position for the bottom of the slinky over time, which I can later plot against my tracker data. This is the graph produced when plotting the GlowScript code against the tracker data. One error causing deviation between the tracker and computer model is tracker error by not consistently marking the bottom of the spring, as the video was low quality and it was difficult keeping track of the same point. Another tracker error is incorrect calibration, as the length of 0.056 meters I used to calibrate the tracker model may not have been correct or even apply to the experiment slinky's dimensions. Furthermore, I could have put the calibration stick at the ends of the slinky when the slinky was not actually fully compressed, because that length of 0.056 meters is at the length I found on the internet for a fully compressed slinky. Another tracker error is using the wrong frame times in tracker, which then affects the times inputted into the computer model, and I believe this is where I made the greatest error, as I did change the time per frame to be smaller when I believe I shouldn't have. An error with my computer model is that the GlowScript code did not account for the small additional applied force from the top of the slinky when it first makes contact with the bottom. And another error may have been an incorrect drag coefficient from obtaining the coefficient through trial and error, and an incorrect mass as it was assumed from the internet. Comparing the data, the tracker data shows a steeper drop than the computational model, which may be attributed by using the incorrect drag coefficient in the computational model, or from all the tracker error, which originated into originally bad tracker data, which then did not match the computer model. Thank you.